Question 18, gaseous nitrogen dioxide forms dinitrogen tetroxide according to the following equation. 0.1 moles of nitrogen dioxide is added to a 1.5 liter flask at 25 degrees Celsius. At equilibrium, the concentrations of NO2 and N2O4 are 0.016 moles per liter and 0.042. Part A, prove that the position of equilibrium will shift to the right after 0.1 moles of nitrogen dioxide is added. Okay, there's a few different ways of doing this. If you're shifting to the right, what that means is the concentration of the stuff on the right increases and the concentration of the stuff on the left decreases. So you can either start by, they've given you the equilibrium concentrations of everything, and they've only given you the initial concentration of the nitrogen dioxide. Now, nitrogen dioxide is on the left. So if you can calculate the initial concentration, if it shifts to the right, then the concentration over time should go down. So if you can calculate the initial concentration and then prove that it's higher than the final concentration, which means it's going down, then it must be shifting away from NO2, so it is shifting to the right. That's the first way of doing it. The second way of doing it is the way we know it from the syllabus, which is calculating the reaction quotient Q and then comparing it to the equilibrium constant K.
Yeah.
Now, part B is calculate the equilibrium constant. So this question is actually worth probably like a few more marks than it needs to be. So normally, if part A was just a single question and they didn't ask you to calculate the equilibrium constant in part B, then we would have gone the Q and K route. That's what you'd normally do in the exam. Or in this case, I might even flip part A and part B. We might rewrite this question and make part B the first part, and then it flows on a bit better.
Yeah.
So normally we would calculate Q and then compare it to K, but in this case, let's do it that first way. Calculate the initial concentration, calculate the equilibrium concentration, and do it that way. So that in part B, we can still calculate the equilibrium constant.
Yeah.
Just based on the way this question is worded. So the initial concentration of NO2, I'll put a subscript I to say that that's initial, is N on V. The initial moles is 0.1. And then the initial volume, or the volume doesn't change anyway, is 1.5 liters. So what's the initial concentration of NO2?
0.06 and then so on.
0.06 ... molar. And then the equilibrium concentration is 0.016. So NO2 at equilibrium is given to you in the question is 0.016 molar. So the concentration decreased, which means the position of equilibrium shifted to the right, away from it. Yeah?
Yeah.
Part B, calculate the equilibrium constant. This one's straightforward. K is concentration of products, N2O4, over concentration of reactants, NO2 squared, raised to the power of the coefficients. And then they've given you the concentrations at equilibrium. So 0.042 divided by 0.016 squared. What do we get for K?
1.5625.
1.5625 ... And then your smallest sig fig, all of them are 2 sig figs. So my final answer, I'll make 1.6, and that's to 2 sig figs. Does the equilibrium constant have any units?
No.
No, it does not. Okay. Question 19. Methane reacts with steam to produce carbon dioxide gas and hydrogen gas according to the equation. 25 moles of CH4 and 25 moles of H2O are placed in an empty sealed 100-liter container at 300 degrees Celsius. After the reaction has reached equilibrium, the container contains 6.12 moles of H2. Calculate the equilibrium constant. Now, interesting thing here is because it happens at 300 degrees Celsius, the water is no longer liquid. So keep that in mind. Normally, water is a liquid and you're used to not calculating a concentration for it, but in this case, you can.
Okay, yeah.
So just watch out for that. So They've given you some initial values. That's what we said when we first did module 5. We said if you get given all initial, you can calculate the reaction quotient. If you get given all equilibrium, you can calculate the equilibrium constant. They've given you some initial and they've given you some equilibrium. So I have to set up an ICE table in this case.
Yeah.
So CH4G plus 2H2OG turns into CO2G plus 4H2G. ICE, your equilibrium constant takes concentration, so it's best to set your ICE table in terms of concentration as well. You could do it in terms of moles and then convert it to concentration after, but it gives you a bit more work later to do. So we might as well do C is equal to N on V at the start. It's easy for this question because the volume is just 100, so it's easy to divide by. So 25 moles of CH4 in a 100-liter container, 25 divided by 100 is 0.25 molar. So that's for CH4. So 0.25 molar, and then H2O, 25 divided by 100, 0.25 molar as well. And then they haven't given you the initial concentrations or amounts of the products, which means we assume that it's
0.
0 because we haven't added it in. Good. And then the last number they've given you, 6.12 moles of H2 in a 100-liter container. So that's about 0.0612.
Yeah.
Okay, so what's the change for H2 going to be?
Is plus 0.0612.
Good. And then it's a 1:4 ratio with CH4. So what's the change for CH4 going to be?
0.0153.
And what sign am I going to use?
Minus.
153 minus. And then CH4 and CO2 is a 1:1 ratio, but it's on the other side. So that'll be plus 0.0153. And then what will the change for the H2O be?
That'll be minus 0.0306.
Yes, 0.0306. So then I plus C gives you E. So what's my equilibrium values?
For CH4 is 0.2347.
Yep.
And then 0.2194.
0.2194. Okay, good. We've got all of our equilibriums now. We can sub it into the equilibrium expression. What's the equilibrium expression for this equation?
That's CO2H2 to the power of 4 on CH4 on H2O squared.
Good. So then that's 0.0153 times 0.0612 to the 4 divided by 0.2347 times 0.2194 squared. What do we get for K?
Um, 1.89, so 1 times 10 to the minus 5.
10 to the minus 5. And then this is 2, 3 sig figs. So that's 1.89. Good. Yes. All right. Question 20. Get rid of this. Carbon monoxide and hydrogen gases synthesize to produce methanol according to the following equation. A, explain the effect of pressure on the yield of methanol. This is a 2-mark question. They haven't specified for me if they want the effect of an increase in pressure or the effect of a decrease in pressure. Explain questions are normally 2 marks. So if I were to do both cases, I'd actually be writing an answer that's worth 4 marks.
Okay.
I might just pick, because they haven't specified, I can just pick myself if I want an increase or a decrease in pressure. And then if I do want to address the other case but not write so much, I might just finish one case and then go vice versa for the other one. just to
Okay,
get
yeah.
it in my answer, but not have to waste time getting extra marks that won't be allocated.
Okay, yeah.
So effective pressure, let's go an increase in pressure. If we increase pressure, what is the system going to want to do to pressure?
Decrease pressure,
Good. And what principle is that according to?
LCP.
LCP, Le Chatelier's principle. So if there is an increase in pressure, then the system will want to decrease pressure according to Le Chatelier's principle. How is the system going to do that? It'll shift to the side with,
Less moles,
good, with less moles of what?
gas.
Yes, less moles of gas. It's going to shift to the side of less moles of gas. In this particular equation, which side is that going to be?
The right,
It's going to be the right-hand side. So therefore shift to the right. And then when you shift to the right, what's on the right? What are we making?
wait, methanol?
Yeah, we're making methanol. CH3OH is methanol. So we're going to increase the concentration of CH3OH. The question's asking you for the effect on the yield of methanol. So if you're making more methanol, then the yield by definition is
Increasing?
increasing. Yeah, because yield is by definition how much you make. So if you're making more, then you're increasing the yield.
Okay, yeah.
All right. Okay, good. Part B, 0.760 moles of carbon monoxide and 0.525 moles of hydrogen were placed to reach equilibrium in a 0.5 liter container. At equilibrium, the mixture contained 0.122 moles of methanol. So some initial, some equilibrium. So this is an ice table question once again. Set up your ice table. CO plus 2H2 turns into CH3OH. ICE. They've given you moles and the volume separately. So once again, I have to calculate that myself. It's 0.76 moles of CO and the volume is 0.5 liters. So what's the concentration?
1.52.
1.52. So that's the initial 1.52. And then 0.525 divided by 0.5 for the hydrogen. What's our concentration for hydrogen?
1.05.
1.05. There's no methanol mentioned at the start, so I assume it's 0. And then at equilibrium, it's 0.122 moles of methanol. So 0.122 divided by 0.5,
0.244.
0.244. So what's my change for methanol?
Plus 0.244.
What's my change for CO?
Minus 0.488. Oh, wait,
So
sorry,
that's
that's four.
H2 minus 0.488. And what about CO?
Minus 0.244.
Yes. 244. And what's my equilibrium for CO? Then I plus C is equal to E.
That's 1.276.
1.276 for H2.
0.562.
562. Then now that I've got everything in the E row filled out, I can sub it into my equilibrium expression. What is my equilibrium expression for this equation?
CH3OH on COH2 all squared.
Yes, CO H2 all squared. 0.244 on 1.276 by 0.562 squared. What is K?
0.6.
0.6, and I want to round that off to 3 sig figs.
0.605.
0.605 to 3 sig figs. Very good. Any questions so far?
No.
No? Okay. Now, question 21. I will 21, 22, 23 have been put in there so that you are aware of it from the syllabus. So these ones I'll direct you to go back to the notes for the lesson recording for. 21 is the experiment you did in class to figure out the equilibrium constant using a colorimeter. Question 22 is dissolving ionic compounds. And question 23 is what Aboriginal and Torres Strait Islander people do to remove toxins from cycad fruit. So these are all things that we've covered together in class or in the notes, and you've already done the proper response for. It's just been put back in here to make sure you revise this syllabus dot point. Yeah.
Yeah.
So feel free to attempt that in your own time, and then feel free to send the response to me so that we can get it marked, but you have done responses for these before when we first covered the content in class.
Okay, yeah.
All right, question 24. Get rid of this. Question 24. 1.9 times 10 to the minus 4 grams of silver chloride dissolves in 100 mils of water. What is the KSP of silver chloride? You are used to subbing molar solubility into KSP. That's what we normally do. Molar solubility is moles per liter. So all we're doing here is linking what we know we need to what they've given us in the question. So we know for us to calculate KSP, we need molar solubility, which is concentration in terms of moles per liter. But in this case, they've given us grams that dissolves in 100 mils. So I don't currently have the information that I need, but I can convert to that piece of information. So KSP is a function of molar solubility. Let's just say MS, and that's in units of moles per liter. I currently have grams per 100 mils, so my job is to convert to moles, convert to liters, and then do C is equal to N on V to get me molar solubility, which I can then sub into KSP.
Okay, yeah.
So from grams to moles, I have to do moles is equal to mass on molar mass. So mass 1.9 times 10 to the minus 4 grams. Ag 107.9, Cl 35.45 grams per mole. So what is my moles going to be?
1.32 times 10 to the minus 6.
10 to the minus 6 moles. And then concentration of AgCl is going to be moles on volume is the 1.32 that I calculated myself divided by the volume. They've told me it's 100 mils, but I need it in liters. So 0.1 liters. What is my concentration?
1.33 times 10 to the minus 5.
10 to the minus 5 moles per liter. The amount that dissolves in moles per liter, that's by definition what molar solubility is. And we're used to giving that the letter X. So let's call that X. And then I'm going to set up my ice table to figure out what KSP is equal to in terms of X.
Okay.
Your KSP, your corresponding chemical equation for KSP has a solid on the left and the ions on the right. So AgCl solid turns into Ag plus aqueous plus Cl minus aqueous. So ICE. Assuming I'm dissolving this in water, that's what they said anyway. They've dissolved it in 100 mils of water. 0, 0 plus X plus X. So this is X and X, which means if I write an expression for KSP, it's Ag plus Cl minus X, X is equal to X squared. So my job now is to just sub this straight in. So 1.33 times 10 to the minus 5 squared.
Yeah.
What do we get for KSP?
1.756 times 10 to the minus 10.
Times 10 to the minus 10. And then I will convert this, the 1.9 times 10 to the minus 4 grams is 2 sig figs. So this is 1.8 times 10 to the minus 10 to 2 sig figs.
Yeah.
Any questions?
No.
Okay. Question 25. Calculate the solubility in pure water of barium iodate, BaIO32 in ppm. That should say iodate, barium iodate. The KSP is 6.0 times 10 to the minus 10. So this is the other way around. Question 24, we did solubility to KSP. Question 25 is KSP to solubility. So instead of subbing in an X, you're rearranging the equation to figure out what X is.
Yeah.
And then it so happens that they want it in ppm. We know that when we get stuff out of the ice table, it's always in moles per liter. So let's get it to moles per liter first, then we'll figure out how to get it to ppm after.
Okay, yeah.
So for me to have my expression for X, I need the chemical equation and I need the ice table. So BaIO32 solid on the left. If I reverse my crisscross method, I get the iodine with a 1 charge and the barium with a 2 charge.
Yeah.
So Ba2, and then metals tend to have the plus charge, so it's Ba2 plus, and then it's IO3 minus. So to balance it out, I need a 2 out the front here.
Yeah.
ICE. They haven't told me I'm dissolving it in a particular solution. They're asking me for solubility in water, which means at the start, the concentration of everything is 0. Water shouldn't have any ions in it. Changes according to ratio plus x plus 2x. So this is x, 2x.
Okay.
And I need to sub this into the equilibrium expression. What's the equilibrium expression?
Ba2 plus and then IO3 minus all squared.
Squared is equal to x, 2x squared, which is equal to 2 to the 2 is a 4.
Yeah.
So this is in total 4x3.
Yeah.
And that's equal to 6.0 times 10 to the minus 10. If they didn't give me a KSP, then I could check it from my data sheet. So rearranging this, x is 6.0 times 10 to the minus 10 divided by 4 and then cube root.
Yeah. That's 5.31 times 10 to the minus 4.
Times 10 to the minus 4. Good. Now, when I get stuff out of the ice table, when I get stuff out of my equilibrium expression, that's always moles per liter.
Yeah.
ppm, we've talked about this before, it's not specified in the syllabus, so if you get asked about this, they need to define for you what the units is. ppm is either milligrams per kilogram or it's milligrams per liter.
Okay, yeah.
So I pick the one that's appropriate for me. I don't have a solid mixture, so I'm not doing it per kilogram of my mixture. I'm doing it per liter of my solution. So I currently have moles per liter. I'm going to try to get to milligrams per liter.
Yeah.
So this is 5.31 times 10 to the minus 4 mole per liter to milligram per liter. We said that we want to convert the numerator separately and then convert the denominator separately. The denominator is already the correct unit, so I don't have to do anything to my number down the bottom.
Okay, yeah.
So the only thing I have to worry about is converting this 5.31 times 10 to the minus 4 moles up the top to milligrams.
Yeah.
I don't normally go to milligrams first. We normally go to grams first, and then we go to milligrams after.
Yeah.
So let's do that. Mass of whatever it is, BaIO32 is moles times molar mass, is my 5.31 times 10 to the minus 4 mole. And what's the molar mass of barium on your periodic table?
137.3.
Yep. And then iodine?
That is 126.9.
126.9, and I have to times that by 2 because my IO3 is in brackets 2. And then oxygen, it's IO3 with a bracket 2. So there's already 3 oxygens and I'm timing it by 2, so that's 6 total. So 16 for each oxygen times 6 for the 6 number of oxygens.
Okay, yeah.
Okay, so pop this in the calculator carefully because it's a big molar mass calculation. What mass for barium iodate do I get?
0.258 grams.
0.258. Mm, This is 10 to the minus 4. That's a pretty big number.
Mm,
What molar mass did we get?
that was 5.3171 times 10 to the minus 4.
That's moles, yeah. What's the molar mass if you just sub this in?
Oh, that's 487.1.
487.1. Okay, maybe it is about right. So 487.1 times 5.31 times 10 to the minus 4 is 0.258.
Yeah.
Okay, that's a pretty decent number. 10 to the minus 4. It's okay. So that's grams. And then we want to convert it to milligrams. Grams and milligrams relates the same way that grams and kilograms do. So 1,000 milligrams is 1 gram, 1,000 grams is 1 kilogram. So when you're going kilograms to grams, you times by 1,000, and likewise when you're going grams to milligrams, you also times by 1,000. So times 1,000 gives you 258 milligrams. And then if I had to convert the denominator, I'd do that separately as well. And then I'd put it back in the fraction. But in this case, my denominator is already the correct unit. So I'll leave. I just had to change the numerator. Once I've changed the numerator, then I can put it back in my fraction. So that's just 258 milligrams per liter. Once I've got the correct units for ppm, milligrams per liter is equivalent to ppm. So I can just change this now, 258 ppm.
Okay, yeah.
Any questions?
Mm,
Okay, good. 26. Calculate the molar solubility of copper 2 carbonate in 0.15 molar magnesium carbonate solution. The KSP of copper carbonate is 2.4 times 10 to the minus 10. They've told you what solution you're dissolving it in. The steps are the same. You just adjust one of your numbers in your ICE table. So step number 1 is to write a KSP equation, chemical equation for the compound that you're dissolving. I emphasize it's for the compound that you're dissolving, not the ionic compound that's in the solution. Yeah. You're getting asked for the solubility of copper 2 carbonate. So I'm writing the equation for copper 2 carbonate, not for magnesium carbonate. Copper 2 carbonate is CuCO3 solid, turns into Cu2 plus aqueous plus CO3 2 minus aqueous. Step number 2, set up your ICE table. The only thing that changes compared to your normal KSP question or your normal molar solubility question is that the concentration of the common ion is no longer 0. One of them will stay 0, the other one won't stay 0. All you have to do to figure out the common ion is to compare the names. Copper carbonate, magnesium carbonate. The common thing is the carbonate. Before you sub the concentration in though, watch out, like we talked about last lesson, they've given you the concentration of MgCO3. You only want the CO3 part. This is a polyatomic ion. You're not looking at the 3 on the oxygen. If I put brackets around the entire CO3, what is the subscript outside of that bracket? How many carbonates are there? I put a bracket around the CO3. I don't have a subscript to tell me how many carbonates there are, but if I were to put one myself, what number would I put right here? I would put a number 1. Yeah, I'd put a number 1 because there's one, if there's no subscript, that means it's a subscript 1. So around the bracket CO3, there's a number 1, which means it's a 1-to-1 ratio of the whole molecule. So if it's 0.15 mgCO3, what's the CO3 concentration? 0.15 as well. Good, because it's a 1-to-1 ratio. So That means the CO3 concentration at the start, before I even tried dissolving anything, is 0.15. There's no copper in MgCO3, so that's still 0. Because the copper is still 0, I am still shifting to the right. So plus x, it's a 1-to-1 ratio, so it's x and 0.15 plus x. Step number 3, as usual, sub in your expressions into the equilibrium expression. So KSP Cu2 plus CO3 2 minus is x 0.15 plus x, and that's equal to the KSP they've given me, 2.4 times 10 to the minus 10. If I were to expand this, I have to solve a quadratic. I don't like solving quadratics. What assumption can I make to avoid solving said quadratic? Yeah, x is way smaller than 0.5. Good. I apologize, hey, I'm just going to use 2 arrows personally because I'm writing it myself. X is way smaller than 0.15. You're not saying that X is small. You're not saying X is small full stop. Just like before, we were talking about relative reaction rate. X is not small full stop. It probably is a small number, but whether or not something is small or big is subjective. So X is way smaller than 0.15. The reason why you don't want to say X is small is because then you'll get rid of this. You don't want to get rid of x, you want to get rid of x next to the 0.15. So x is way smaller than 0.15, so this becomes x 0.15 is equal to 2.4 times 10 to the minus 10. So then x is 2.4 times 10 to the minus 10 divided by 0.15, which gives me 1.6 times 10 to the minus 9 to 2 sig figs. What's the units? KSP has no units. Does x have no units? X is from the ice table. It's taking concentrations. That's moles per liter to 2 sig figs. Good. Any questions, please let me know. I know common ion effect was one of the things you guys pointed out, which is why we're doing it. Question 27. Calculate the molar solubility of chromium 3 hydroxide in a solution with a pH of 8.4. The KSP of chromium hydroxide at 25 degrees Celsius is 6.7 times 10 to the minus 31. If we were asked why we made that assumption, what would we say? You would say that KSP is a really small number. It has a magnitude of 10 to the minus 10. So then if KSP is a function of x. So then if KSP is really small, then x is going to be a really small number as well. So KSP, very small. So you can assume that the numbers that go into making KSP are also very small. Now, before we go into question 27 together, what's the common ion? Hydroxide. Good, well done. Okay, now let's say, because you know this is a common ion effect question because I told you, then there's 2 options, yeah? The common ion effect is one of the 2 ions that you're dissolving. So it's either chromium or it's either hydroxide, which means from there you figure out, based on the information in the question, if you can get the chromium concentration somewhere or if you can get the hydroxide concentration somewhere. The only other information they've given you is pH, which is a function of proton concentration, which can be converted to POH, which is a function of hydroxide concentration, which means the common ion is the hydroxide. But then let's say you're in the exam and you read this question yourself and there's no label that tells you it's a common ion effect question. The alternative then is, you've been exposed to this question, so you don't have to deal with it. But the alternative in the exam, if you don't have a label that says it's a common ion effect question, is to annotate the question and see what information you get out of it. So if you just scribble around and see what you can do with pH, you'll get POH. POH is 14 minus pH. POH is negative log base 10 OH minus. And then as you're brainstorming, hopefully you notice the hydroxide in this name and the hydroxide that came out of your pH brainstorm. And then you're like, hold on, I have a hydroxide in one place, but I have a hydroxide in another. This might be a common ion effect question. So that's the way you go about it in the exam. Now, let's say question 27 is familiar enough to you that you're like, I'm not concerned. And I can't tell that this is a unique question because when you read question 27, it looks pretty doable. It's like, I can do that. So what you can do then is you'll go about your motions the same way, set up your KSP equation, set up your ice table. And then when you get up to your ice table and you start filling in the numbers, then you might realize at that point that you haven't subbed in your pH concentration yet. At which case you're like, oh, at first when I read the question, it kind of seemed like I know what I was doing. But when I'm confronted with having to do the actual working out, I don't know what I'm doing. And then you can do your brainstorm process as you've already started your working out. Yeah. So if a question is unfamiliar enough to you, then you'll know to brainstorm and label stuff at the beginning. But if you don't, and it sounds familiar, that's fine. Go ahead and do what's familiar to you. And then when you realize you have to stop, then you're allowed to brainstorm as you go throughout. So let's do that. Let's say I read question 27. It looks familiar enough. Don't really know what to do with the pH yet, but I'm not anxious enough about it to brainstorm everything. So I'll start. I know that when I normally get asked for molar solubility questions, my first task is to write out the equation. And then my second task is to set up the ice table. And then when I go to set up the ice table, my normal motions is to go this and this. But then I realize in the exam that I'm like, hey, hold on. This is the start of where I put in my numbers. I have to be conscious of the numbers they've already given me in the question. And then I get confronted with the fact that I actually don't know what to do with this pH. So I'm going to need to start brainstorming it now just in case it does go into my ice table. So pH is negative log base 10 of H plus, which is 8.4. And then as I do that, I'm like, pH doesn't relate to chromium. pH doesn't relate to hydroxide. But if you've had enough experience with Module 6 calculations as well, pH can be converted to POH is equal to 14 minus pH is equal to 14 minus 8.4. If I'm using POH is 14 minus pH, what temperature am I operating at? 25 degrees Celsius. Good. I'm allowed to do that because the KSP they gave me is also at 25 degrees Celsius. What is POH equal to? 14 minus 8.4. What do you get for that? 5.6. And then POH is negative log base 10 of OH minus. And then I realize, hey, hold on. Now that I've done some brainstorming, my ice table takes concentration. I now have concentration of hydroxide. And that's when your heart starts beating in the exam. And you're like, dang it, I just came across a common ion effect question. So OH minus is 10 to the minus 5.6. So that now goes up here. 0 plus x plus 3x, because there's a coefficient of 3. So this is x, 10 to the minus 5.6 plus 3x. And then the rest of your steps are the same. Sub it into your equilibrium expression, Cr3 plus OH minus to the 3, which is x, 10 to the minus 5.6 plus 3x is equal to the KSP they've given you, 6.7 times 10 to the minus 31. And you're going to go KSP very small. So I can assume 3x is way smaller than 10 to the minus 5.6. So then this is just approximately x, 10 to the minus 5.6 without the 3x now, and that's to the power of 3 is 6.7 times 10 to the minus 31. rearranging this. 6.7 times 10 to the minus 31 divided by 10 to the minus 5.6 with a power of 3. Guys, please pop this into your calculator carefully. What do you get? 4.2 times 10 to the minus 13. Give me a thumbs up if you got the same answer. Minus 5 by 3 is about a 15. So you should be that. Oh, sorry, 14. What am I doing? And that's 2 sig figs. This is X, so you get units of moles per liter. Okay. Can I get a thumbs up, guys? Does this make sense? From pH, you can get pOH, which is a function of hydroxide concentration. Your ice table takes hydroxide concentration, which is how we know this is a common ion effect question. You are allowed to brainstorm as you do your working out when you realize when you realize that you don't understand something. It doesn't have to happen at the start. Yeah. Okay. Take a 5-minute break for me. 7:38 we'll come back. If you have any questions about module 5, let me know. If you have anything you're dying to do for module 6 that you haven't told me about yet, let me know. 7:38, we're gonna start on your module 6 sheet. All right, let's move ahead. We'll have a look at question 28. Will a precipitate form when 10 mils of 0.005 molar barium chloride is mixed with 20 mils of 0.002 molar sodium sulfate? Support your answer with calculations. So this question 28 is not a difficult question in the sense that there's lots of thinking to do, because it's one of the questions where the step-by-step is pretty straightforward. So this is just revision of the steps. So question 28, step 1, write your chemical equation for the precipitation. What's the formula for barium chloride?
BaCl2.
BaCl2. What's the formula for sodium sulfate?
Na2SO4.
Na2SO4. The ions will swap and you'll make the stuff on the right. So you'll make barium sulfate, BaSO4, and then you'll make sodium chloride, NaCl. So from your solubility rules, which one is the precipitate?
Barium sulfate.
Good. And then NaCl is still aqueous. Okay, how do we balance this equation?
Put a 2 in front of NaCl.
Yes, put a 2 in front of NaCl. Okay. Will a precipitate form depends on you satisfying the inequality? We talked about this with one of the earlier questions as well. In one of the earlier multiple choice questions in this sheet, we want QSP to be greater than KSP. And then that only works for the precipitate. So if you know that the precipitate is BaSO4, then you look for the KSP of BaSO4. And then also you need KSP of BaSO4 takes in the barium concentration and the sulfate concentration.
Yeah.
So that's what you're determining the concentrations of when you mix it together. We really don't care about the concentration of the chloride anymore. And we also don't care about the concentration of the sodium anymore.
Yeah.
So step number 2, when you're mixing solutions together, you are diluting it, because the moles has stayed the same, and then you're dividing by a bigger volume because you've mixed 2 volumes together. So we can use the dilution formula in this case. C1V1 is equal to C2V2.
Okay, yeah.
Then C2, the final concentration that we're looking for, is C1V1 on V2, where V2 is the total volume of the 2 solutions.
Yeah.
All right, so we said the precipitate is BaSO4, so we're concerned with Ba2 plus and the SO4 2 minus.
Yeah.
Now, so concentration of Ba2 plus, C1V1 on V2. Once again, they actually haven't given you the concentration of just the barium. They've given you the concentration of the barium chloride. So we want to check if it's a 1-to-1 ratio or if we have to multiply by anything.
Yeah.
How many bariums in barium chloride?
1.
One. So it is a 1-to-1 ratio, which means I can take this concentration of barium chloride and say that's the same as the concentration of barium.
Yeah.
But if I was, for example, looking for the concentration of the chloride, I would have to take this concentration and times it by 2, because there's a subscript 2 on the chlorine.
Yeah.
But right at the moment, it's fine. I can take it as is. So C1 is the 0.005. And then V1, the initial volume is 10 mils, 0.01 liters. The final volume, once again, we said is the total volume. 10
Mm,
mils from the barium chloride, 20 mils from the sodium sulfate. So the total volume is 30 mils, which is 0.030 liters.
Yeah.
So what's my concentration of barium ions when I mix the two solutions together?
1.66 times 10 to the minus 3.
10 to the minus 3 mole per liter. And then now remember, the whole point of doing this is so that you can sub it into KSP later, but KSP takes in the barium concentration as well as the sulfate concentration.
Yeah.
So you're going to need this number later, which means when you have this knowledge in your head, save it in the calculator from the get-go so you don't have to type this out again afterwards.
Yeah.
Same thing for the SO4 2 minus. I, once again, haven't been given the sulfate. I've been given sodium sulfate. So I need to check what's the ratio. How many sulfates in sodium sulfate?
1.
One as well. So if I put those brackets around, the invisible subscript is 1. So I can take the concentration of the sodium sulfate, 0.002, as the concentration of just the sulfate as well.
Yeah.
So C1, V1 on V2. C1 is 0.002 molar. V1 for the sodium sulfate is the 20 mils, so 0.02 liters, over total volume is the same once you've mixed them together, 0.030 liters. So what's my concentration of sulfate?
1.33 times 10 to the minus 3.
10 to the minus 3 moles per liter. And then now that I've got the two concentrations, I need to sub it into the QSP expression for my precipitate.
Yeah.
But for me to do that, I need to know what the equation is. It's a 1-to-1 ratio. So QSP has the same expression as KSP. I'm just subbing in different concentrations. So it's the 1.66 by 10 to the minus 3 that I calculated, the 1.33 times 10 to the minus 3 that I calculated. So what's the QSP for BaSO4?
2.22 times 10 to the minus 6.
Times 10 to the minus 6. And then for a precipitate to form, I need QSP to be greater than KSP. They haven't given me the KSP in this case. Where do I go looking for it?
The data sheet.
The data sheet. Let's go look for it there. Periodic table. Let's go. HSC datasheet chemistry. And what's the KSP for barium sulfate?
1.08 times 10 to the minus 10.
1 point. KSP is 1.08 times 10 to the minus 10. Our QSP that we calculated is 10 to the minus 6. So is QSP bigger or smaller than KSP?
Smaller.
Smaller, 10 to the minus 6 is our QSP, not our KSP.
Oh, QSP is greater.
Yes, 10 to the minus 6 is greater than 10 to the minus 10. So QSP is greater than KSP. So does a precipitate form?
Yeah.
Yes. Precipitate forms. Okay, good. Any questions?
I'm just confused about like why you can use the C1 V1 on V2 formula.
Yeah, that's all good. Now, the reason why when we first learned this together, I actually didn't use the C1 V1 C2 V2 with you. So you would have remembered when we did it together, we did C1 times C times V to get the moles, and then we divided it by the total volume.
Oh, okay.
Yeah, which is actually the same thing. C1 V1 on V2. Yeah. So the reason we haven't used it before is because whenever we've done other questions involving dilution, like when you did it in module 6, there was always like, oh, dividing the volume first and then you dilute it afterwards. So the reason I didn't like doing it with you then was because the volume changed so much, you wouldn't always use the dilution formula. So I didn't like telling you it sometimes and not telling you at other times. So we kind of just like stopped using the dilution formula after year 11. But in this case, when you're doing does a precipitate form, you never really stray away from this equation, which is why you can use it.
Okay.
So the whole purpose, all we're doing here is trying to find the mole stays the same, but in a new volume. So that's why you do C times V to get the moles, and you divide it by the total volume afterwards, which
Okay.
is exactly what a dilution formula is for. If you don't change the moles, but you're making the volume bigger, that's by definition what dilution is,
Okay, yeah.
which is why we can use it.
Okay, thank you.
That's all good. Anything else?
No.
All right. Last question 29. Determine if a precipitate will form when 75 mils of a sodium hydroxide solution is mixed with 125 mils of a 0.018 molar magnesium chloride solution. The pH of the sodium hydroxide solution is 11 at 25 degrees Celsius. So, question 29 is ever so slightly different from question 28. They've given you 2 volumes, but they've only given you one concentration. They haven't given you the concentration for the sodium hydroxide, but they have given you its pH.
Okay, yeah.
And you know from module 6 that if you have the pH of an acid or a base, then you can go back to find the concentration of it.
Yeah.
So this is just an additional step.
Yeah.
Yeah, and then we follow the rest of the steps the same way that we did with 28. So, step number 1, write your balanced chemical equation again so that we can figure out what the precipitate is. What is the formula for sodium hydroxide?
NaOH,
NaOH. What's the formula for magnesium chloride?
MgCl2.
MgCl2. And then we form NaCl and we form magnesium chloride, MgOH2. From your solubility rules, which one's going to be your precipitate?
The magnesium hydroxide.
Yes, the magnesium hydroxide. So then when we go to determine KSP, figure out QSP, that's going to be for your magnesium hydroxide. So number 2, once you've identified your precipitate, then you know what moles you're looking for. You're not looking for the concentration or moles of the sodium or the chlorine, because that doesn't form your precipitate. You're looking for the moles and the concentration of your magnesium and your hydroxide.
Yeah.
Okay, now once again, this isn't the concentration that it came in. This is the final concentration after you've mixed the 2 volumes together.
Yeah.
So we need to use our C1V1 is equal to C2V2 equation, because after you mix them together, the volume gets bigger, so it gets more diluted. That's why we use the dilution formula.
Yeah.
And once again, similar to question 28, V2 is just the total volume.
Yeah.
Now, we said we don't get given the concentration of the sodium hydroxide. We have to do a pH calculation for that. So that'll take a little bit longer. We can do it, but let's get the easier stuff out of the way first. Let's say you're in an exam and you're running out of time. You want to get as much down as you can.
Yeah.
Leave that for now. So we'll do the magnesium chloride first. Concentration of Mg2 plus. Once again, we're looking for Mg2 plus only, but we get given magnesium chloride. So I just want to check the ratio. How many mg's in magnesium chloride?
1.
1, it's a subscript 1. So I don't have to multiply the concentration by anything. I can take the 0.018 magnesium chloride as 0.018 just for the magnesium as well. So that's C1, that's 0.018 molar. V1, it started off as 125 mils, which is 0.125 liters, over. The total volume is when I add them together. 125 plus 75 is 200 mils total, which is 0.2 liters. So what's my concentration of Mg2 plus when I mix it together?
0.01125.
0.01125 molar. Good. And then hydroxide, same thing. I need to do C1V1 on V2, but I don't have C1 because they haven't told me the concentration of the sodium hydroxide.
Yeah.
I have to get that from the pH. Now, is sodium hydroxide a strong base or a weak base?
A strong base?
It's a strong base, which means I don't have to worry about like equilibrium constants and ice tables, things like that. So when I go to get the concentration of the hydroxide from my pH equation, I can take that as the concentration of the sodium hydroxide.
Okay, yeah.
Because it's strong, it dissociates completely. So however many hydroxides I have, that's all of the hydroxide that came from the sodium hydroxide.
Yeah.
So I don't have to worry about an ice table and things like that. So we've already established sodium hydroxide is a base, which means I don't want to work with pH. I want to work with
POH?
POH. Good. Now, how do I get POH from pH though?
14 minus 11.
Good. 14 minus pH is 14 minus 11, which is equal to 3. And then what's the equation for POH normally?
The 10 to the, oh, sorry, negative log base 10 of the concentration of OH minus.
Yes, good. And then if I were to rearrange this, what would OH minus be?
10 to the minus POH.
Yes, 10 to the minus POH, and then POH is 3, so OH minus is 10 to the minus 3.
Yeah.
And then there's a 1-to-1 ratio. I need to check the formula. NaOH, if I put brackets around the OH, it's 1 OH per NaOH, which means it's a 1-to-1 ratio, so the concentrations are the same.
Yeah.
So this is also the concentration of the NaOH.
Yeah.
So now that I've got the concentration of the NaOH, I do the same thing that I did with the Mg2 plus, the C1V1 on V2.
Yeah.
So OH minus is what goes into my precipitate. So C1 is, I had to calculate myself, 10 to the minus 3 molar. V1 from the question, 75 mils, 0.075 liters. V2 is the total volume once you've added them together. It's the same for each of them, 0.2 liters. What is OH minus equal to?
3.75 times 10 to the minus 4.
3.75 times 10 to the minus 4 molar. Now that I've got both things, I can sub it into my KSP equation, KSP expression. But for me to know that, for me to write the equilibrium expression, I need to know what the equation looks like. So I have to write the KSP equation. So MgOH2 solid turns into Mg2 plus and OH minus.
Yeah.
And I have to balance this equation. How do I do that?
2 in front of OH minus.
Yes, good. The 2 is important because it goes into the powers of my equilibrium expression. So I'm calculating QSP actually. Well, it has the same expression, but I'm calculating QSP. What's the expression for QSP?
Mg2 plus and then OH minus all squared.
Yes, OH minus all squared. So now I can sub my numbers in. Mg2 plus, I got 0.01125. I got 3.75 times 10 to the minus 4. That's squared. So what is QSP equal to?
1.58 times 10 to the minus 9.
10 to the minus 9. I have to check if it's greater than KSP. They haven't given it to me in the question, so I have to go find it myself. What's the KSP for magnesium hydroxide?
5.61 times 10 to the minus 12.
Okay, so are we bigger than KSP or no?
Yeah.
Yes, we are. So QSP is bigger than KSP. So do we form a precipitate?
Yeah.
Yes, so our PPT will form. Okay.